Today we're going to evaluate the sum from n equals 1 to infinity of n to the third over 3 to the n. So try it on your own and let me know in the comments if you're able to solve it, or you could just watch me solve it. Okay, so in order to evaluate this sum, we're actually going to consider a slightly different sum. So let's consider the sum from n equals 1 to infinity. So instead of n to the third over 3 to the n, let's look at the sum of n to the third times x to the n. Okay? And then what we're going to do is we're going to evaluate at x equals 1/3 to get back our original sum. Okay, and so what we want to do is we want to find what function has this series as a power series. Okay, so once we figure that out, then we can evaluate at x equals 1/3, and we're done. So let's consider the function f of x, which is equal to x over 1 minus x. Okay, and why are we doing that? This has a really nice power series. So you'll learn in Calc 2 that for x, when x is between -1 and 1, this is equal to the sum from n equals 1 to infinity of x to the n. Okay, it's n equals 1 because we have this additional factor of x on the top. Okay, and so maybe I'll do a video in the future explaining why this is true, but for now, you just have to trust me if you haven't gotten to that stage in your math career. Okay, and so this looks pretty close to here, except there's an n to the third in these terms. So what we could do is we could take the derivative of this function, f prime of x. Okay, and the derivative we could get with the quotient rule, so that's 1 minus x times 1 minus x times -1 all over 1 minus x squared. Okay, and this simplifies to, well, we have negative x plus x. So we're just going to have a 1 in the numerator, and the denominator is 1 minus x squared. Okay, and what is this equal to? It's equal to the derivative of this series here. So that's the sum from n equals 1 to infinity. We bring the power in front and drop 1 from the power. Okay? And our series has an exponent of n. This has an exponent of n minus 1. So if we multiply both sides by x, we'd get the exponent that we want. So we have that x over 1 minus x squared is equal to the sum from n equals 1 to infinity of n x to the n. Okay, we're making some progress, right? We want n to the third. So let's find the next derivative. So f double prime of x, and now we're taking the derivative of this function here. We're not taking the derivative of the x times f prime of x. F double prime of x, you know, you could do this on your own. It's just 2 over 1 minus x raised to the third power. Okay, and that's equal to the derivative of this series over here. So the sum from n equals 1 to infinity of n times n minus 1 x to the n minus 2. Right? And now using a similar argument as before, we can multiply an x squared to both sides. And we have that the sum from n equals 1 to infinity of n times n minus 1 times x to the n is equal to this function. Okay? And if we were to multiply this out, we'd have an n squared minus n times x to the n. So we could actually clean this up a little bit more, but we won't do that for now. We'll do it in the next step. All right? Because here, like, the highest power is n squared. We want n to the third still. So let's do one more derivative, and then we should be there. So f triple prime of x is equal to the derivative of this function, which is 6 over 1 minus x to the fourth. And that's equal to the sum from n equals 1 to infinity of, we'll bring the power in front again. So n minus 1, n minus 2, x to the n minus 3. Okay, and now let's multiply both sides by x to the third. So we could have just x to the n again in our sum. Okay, so we have that 6x to the third over 1 minus x to the fourth is equal to the sum from n equals 1 to infinity of n minus 1, n minus 2, x to the n. Okay, so I'm going to clean this up a bit, and then we'll solve this problem. Okay, so this is what we had, and I noticed I had a little bit of a typo here, so this fourth should actually be on the outside if we did the derivatives correctly. Okay, so sorry about that. Again, we want to get the sum from n equals 1 to infinity of n to the third x to the n. So let's multiply this out. So this term here is the sum from n equals 1 to infinity of n to the third minus 3n squared plus 2n all times x to the n. And that's equal to this 6x to the third over 1 minus x to the fourth. Okay, so let's bring over some terms. And we have that the sum from n equals 1 to infinity of n to the third x to the n, so that's what we're trying to evaluate, is equal to 6x to the third over 1 minus x to the fourth plus 3 times the sum from n equals 1 to infinity of n squared x to the n minus 2 sum from n equals 1 to infinity n x to the n. Okay, and so we're going to want to use this term here, but this is n squared minus n times x to the n gives us this formula. Here we just have n squared. So what we could do is change this 2, instead of having minus 2 times this term, let's make it minus 3, and then we'll have to add a copy of it. So minus 3, sum from n equals 1 to infinity of n x to the n, plus the sum from n equals 1 to infinity of n x to the n. Okay, this is already done. This here is just 3 times this, and this here is just this. So our sum is equal to 6x to the third, 1 minus x to the fourth, plus 3 times this. So plus 6x squared over 1 minus x to the third, and then plus x over 1 minus x squared. Okay, and so now putting it all together, when we sub in x equals 1/3, we have the sum from n equals 1 to infinity of n to the third over 3 to the n is equal to, and now we just sub in x equals 1/3. So 6 1/3 to the third over 2/3 to the fourth, plus 6 1/3 squared over 2/3 to the third, plus 1/3 over 2/3 squared. And when you type all of that into a calculator or evaluate it by hand, you get 33 over 8. Not bad. So this shows the power, pun intended, of power series. So power series are very useful for evaluating series. Thanks for watching, and let me know if you liked the video.